Good day, learners. Welcome to Technical Sciences lesson. My name is Zamisile Mdima. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. So today is our first lesson on waves and sound. So we're taking it easy. We just want to know the terminology. We want to know the difference between a wave and a pulse. So we are just going to go through it together. Okay. So here is going to be our focus on waves and sound. We're going to be looking at the definition for pulse. We're going to be looking at different types of pulse that are, and then we're going to be looking at the wave. We're going to be looking at the superpositioning. We're going to be looking at the MCQ as well as your long type of question. So let's get started. So what is a pulse? You may ask yourself. It is a single disturbance that moves through a medium. Okay? And then I know you are asking yourself once more, what is a medium? Now, a medium is a substance or material through which a pulse is able to move. Okay, now a medium carries the pulse from one place to another. Okay, just to give you an example of a pulse, you will fill your bowl or a very big dish. Okay, just put it water inside, and then now throw a small drop or a small stone inside it. What you will see is that there will be a disturbance in that medium. Now, water then serves as a medium, and then the stone that you put into that quiet waters is a single disturbance that disturbs these quiet waters. Now, a medium is a substance through which a pulse moves. So due to that stone that you put inside, it's thereby created what? It created a pulse. Okay. Now a medium, as I've said, it carries the pulse from one place to another. So you will notice that even if you're putting your stone in one position, but it will create segment of these disturbances from one place where it was thrown to another place into the edge of this dish. Okay, now the medium does not create the pulse. But what do we mean by that? Before you threw a stone into this quiet water, there was no disturbance. So the medium itself, the water itself, because in this case, water serves as what? As a medium, because now pulse was able to move through, being carried by what? From one point to another, using what? Using a pulse. Okay, so now a medium does not create the pulse, but the medium is not the pulse, but you are just creating a single disturbance into that medium. Therefore, the medium, we say, it does not travel with the pulse as the pulse moves through it. The pulse is moving on its own, and it uses the medium as a source of moving from point A to point B. Okay, in each medium, the particles that make up the medium are moved temporarily from their rest position. Okay, so before you even threw a stone, everything was at rest. So we call that a rest position, or you can call it in equilibrium. But the minute we start now throwing a stone inside the water, it creates that single disturbance that moves through the medium. That means that your medium particles are not now at rest. They have shifted from their rest position. Okay? So that is why we say, in order for a pulse to travel, the different parts of the medium must be able to interact with each other. And when we say the medium, we can say the examples of what? Of air. So air can serve as a medium, water, solid substance. So in all the phases, whether it's a gaseous phase, it's a liquid phase, or it's a solid phase, all those substances could be a medium, meaning they are able to what? To allow the pulse to move through it. All right. So that is a pulse. It is a single disturbance that moves through a medium. What are the examples of the medium? You can ask yourself. It can be air, it can be water, it could be a solid substance. And what is the main function of a medium? Okay, the main function of the medium is to allow the pulse to move from one place to another. However, bear in mind that the medium does not create the pulse. It just allows it to move from one position to another. Okay? So, there are two types of pulses that there are. So, we've got a transverse pulse and we've got a longitudinal pulse. But before we even get into the longitudinal pulse, what is a transverse pulse, you may ask yourself. Now, a transverse pulse is a pulse in which its particles of the medium, they vibrate at what? At right angle to the direction of the propagation of the pulse. So they move up and down to the propagation of the pulse. So that is what we mean, what we say at right angle to the direction of propagation of the pulse. So there's a nice diagram over there that is showing us how it will move up, and here is your propagation of the wave. So the particles of the medium are going up, and then the propagation of the wave is going in that direction. Hence, it is creating that right angle, which is a 90 degrees angle. All right. So initially, the rope was at rest. All right, was a horizontal position, which we call it a rest position. But a single disturbance had created the movement in which the perpendicular to the origin of motion. Okay, so that is why, as you can see, the rope is shifting up a little bit. However, the propagation of the pulse is going in that direction. Okay, now then when we refer to the rest position, we mean that it was just horizontally. It was at rest. There was no disturbances, because by definition, a pulse is a single disturbance in a medium. All right. So we elaborate further on saying the rest position is the position the medium will be if it is left undisturbed. Now, this is called equilibrium position. So your equilibrium position as well as your rest position is one and the same thing. Now, in a transverse pulse, which is the one we are referring to right now, displacement of the medium is perpendicular to the direction of the pulse, which is very important. What we're saying is the displacement of the medium. So that, remember, the word displacement refers to the what? To the change in position. Okay, so as your medium changes the position in a perpendicular manner, it will change position to the perpendicular to the what? To the direction of motion of the what? Of the pulse. Okay, hence creating that what? For the particles in the medium to vibrate at the right angle. Okay. However, remember we said we had two types of pulses. The first one we just spoke about, which is your what? Which is your transverse pulse. Now we're talking about a longitudinal pulse. How is it different to the transverse pulse, you may ask yourself? It's a pulse in which the particles of the medium vibrate parallel to the direction of the propagation of the wave. Now, when we say parallel, it's one on top of another, in the same direction. Remember, with your transverse wave, is that the particles of the medium will vibrate at the right angle, perpendicular to the propagation of the wave. However, on the longitudinal pulse, the particles of the medium, what you are using for the pulse to be able to move from one point to another point, is vibrating in a parallel position to the direction of the propagation of the wave. How so? Let's look at this diagram. You've got the energy of the wave moving in that direction, meaning that the propagation of the particles in the medium are vibrating to the parallel, as well as the direction of the pulse is moving in that direction. Okay, so how do we then sum this up? So a best example for the longitudinal pulse is your spring. As you can see, as you are shaking it without moving it up and down, as you are shaking it, you will see that there will be spaces of compression whereby your spring is being contracted and whereby it is far apart, compressed and far apart. That is your pulse moving from one position to another position, from one position to another position. Okay, and it's propagating parallel to the vibrating of the medium particles themselves. Now, in a longitudinal pulse, the displacement of the medium, particles of the medium that is, it is parallel to the what? To the direction of motion of the pulse. So that's how we can learn to differentiate between the two. So on the transverse pulse, you may use, for example, a string. You just create a single disturbance. Here is our single disturbance over here. That is your pulse. But now, it causes the particle of the medium to vibrate at what? At the right angle to the propagation of the wave. Okay. Then we have a wave, right? Remember, with your pulse, it's just a single disturbance. You just call it a single disturbance, just one disturbance in the medium, okay? And we just spoke of water that was in quietly in a beaker or in a dish or big dish, and then you just inserted what? Dropped a small stone. Now, how is then a pulse different from a wave? You may ask yourself. A wave is a periodic now, continuous disturbance. You're not only just a single disturbance, but now it's just a continuous disturbance that causes a train of successive pulses. So you've got pulse of another pulse of another pulse. It's no longer just one pulse moving from one position to another position, but now it's just a continuation of these single disturbances causing a train of succession of pulses. The word succession means one after another, one after another. So now creating this periodic continuous disturbance in that medium. Okay, just like with pulses, you've got two types of waves. Okay, you've got your transverse wave and also you've got your longitudinal wave. First, let's explore your transverse wave. Okay, a transverse wave has the particles of the medium vibrating at the right angle to the direction of the propagation of the wave. So you'll see that these definitions are the same. So your definition of a transverse pulse and your definition of a transverse wave are the same. But now, what is the difference between the two? A wave is a continuous disturbance. It consists of a train of successive pulses. A pulse is a single disturbance. Okay? In a transverse, your particles of the medium, whether you're talking about a pulse or you're talking about a wave, it causes the particles of the medium to vibrate at right angle to the propagation of the wave. Okay, so I just showed you a nice illustration of the wave motion. That is the propagation of the wave. But going up on the side, it is showing the particles of the medium vibrating at right angle. So particles of the motion are vibrating at right angle, but here is the propagation of the wave creating that 90 degrees angle. Hence, we're saying it's at a right angle. Okay. Now, for waves, there is no displacement. They return to their equilibrium position. And what do we mean by that? They can go up and go back to their equilibrium position. They can go down and go back to their equilibrium position, because now it is a continuous what? Disturbance, and has a continuous succession of pulses. But there is no net displacement. What you find is that there are just two motions. Okay, the motion of particles in the medium. Hence, we've got the motion of particles in the medium being perpendicular to that of the propagation of the wave. All right. So here's a detailed label transverse wave. You've got your crest, you've got your trough, you've got your amplitude, you've got your wavelength. But then now, how do you then define all these terms? And how do you see that this one is a crest, this one is a trough? This is how I properly identify my amplitude. This is how I see that this is the wavelength of my wave. Okay, so a crest is the uppermost point on a transverse wave. Okay, when we say the uppermost, you're going up. Okay, from the rest position, is it the uppermost point on the transverse wave? Okay, and then the trough is the lowermost point on the transverse wave. I usually say, when you are mentioning your alphabet, you say your A, B, C. C comes first. C is always going to be the uppermost point of your transverse wave. Comes first. Okay? But as you continue with your alphabet, T is right at the end. It's always going to be the lowermost point on a transverse wave. Okay, remember we had referred to say the equilibrium position is the same as your what? As your rest position. Okay, so this is where your wave is resting. So this is what? Your rest position. Right. Okay, we also have an amplitude. What is an amplitude, you ask yourself? Amplitude, it is the maximum. So let's start by saying both your crest as well as your trough will have an amplitude. So it's a maximum displacement because there was a change in position from the rest position to the uppermost or from rest position to the lowermost. Okay, you can have your amplitude in your trough. You can also have your amplitude in what? In your crest, right? And then you have your wavelength. Your wavelength, it is the distance between two successive what? Pulses that are there. But first, let's just look at the crest, the trough, as well as your what? Your amplitude. Let's move right along as we explore also the wavelength in detail, the amplitude as well in detail. Right. And then before we get into that, we have a longitudinal wave. How is it different from a longitudinal pulse, you may ask yourself? It is still the same. However, now remember that a wave, it is made up of continuous disturbances that are there in your medium. Okay, this is why we say a wave, where the particles in the medium move parallel to the direction of the propagation of the wave. So here's a string. String is propagating in this direction. The particles of the string are also moving into that direction. Hence we say the propagation of the wave and the particles of the medium, they move parallel against one another. Okay, so how can we best draw this longitudinal wave? We use it lines. So where they are closer to each other, and there we put lines that are close to each other. And when they are far apart, where your string is far apart, moving the pulse from one position to another, here is far apart, and also here it is far apart. Okay, but now longitudinal waves can be represented by vertical lines closer together and far apart. But now what do we refer to these closer together lines, far apart lines? Okay, so when the lines are closer to each other, we refer to them as being what? There is a compression. So here is our compression over here. Right, and when they are far apart, we refer to them as what? As rarefaction. So here's our rarefaction area. Okay, now a distance between one compression and to another compression will be our wavelength, and we give our wavelength to being what? In meters. Okay, and even if you're not looking from the compression to compression, you're looking from the rarefaction to another rarefaction, it still marks your wavelength. Okay, so this is a detailed labeled longitudinal wave. There are many important terms, but we're going to run them step by step so that all of them, you understand them even diagrammatically, so that by the time you have to identify them in a test or an exam, it is very easy for you. Okay, let's begin with the amplitude. It is the maximum displacement of a particle from its equilibrium position. Maximum displacement. It does not mean it will be applicable to a crest only. It can also be applicable to what? To a trough as well. Let's just go back a little bit so that we just show this very nicely. It is the maximum displacement from the rest position. Remember, we said it is there, it is in a trough, and there it is in a crest, right? Okay, we've covered this one together. And the wavelength, the distance between two adjacent crests, is the same no matter which adjacent crest you choose. Okay, let's put it in practice. So here's your crest, and here is your crest over here. So you have your crest, and then now we're saying it is the distance between two adjacent. So they have to be following each other, okay? Distance between two adjacent crests, which is the same no matter which adjacent crest you choose. For example, on the other side, we're choosing the two troughs as well. So, but they have to be adjacent to each other. They have to be following one another. So there's a trough and there's a trough. And the distance between these two troughs then we refer to as what? As your wavelength. Don't forget the SI units from the grade 10. Because we're talking about the length, therefore it has to be measured in what? In meters. We sometimes refer to them as lambda. This is the symbol we give it. It's a Greek name, lambda. And this is the symbol, just to write it more nicely. Okay? And then points in phase. Okay, so in your wave, how do you then identify the points that are in phase and the points that are out of phase? Let's start with the points that are in phase. 2 points are in phase when they are in the same state of vibration. What do we mean by that? Let me move a little bit. I want to show this nice diagram because now it has points in them. Okay, so that we are able to say, okay, point B is in phase with point H. Okay, so now let's first identify the points that are in the same state of vibration. Okay, so point B in phase. Okay, let me write in phase using black because they are in phase. They are in the same state of vibration. In phase, you have your B and H. So, mind you, they're in the same state of vibration, meaning you can't just say B. It has to go in pairs. It has to be a certain alphabet alongside with another alphabet. That means you have looked at both and their states of vibration, and you said, okay, these two are in the same state of vibration. Another one will be your C and F. Here's your C, here's your F. They are vibrating in the same position. Okay? Someone else can say F and I. Someone else can come and say, okay, another ones that are in the same state of vibration will be your what? Your C and I. Remember, C, you see, and C, your I over there. Right. So all of these points are in phase because they are in the same state of vibration. Okay. And then we have your out of phase. Before we are able to, or we identify them, let's just first take a look at the definition. 2 points are out of phase when they are not on the same state of vibration. Okay? Now let's go back to our points. Let's identify the ones that are out of phase. You have your H and E. Your H is right there at the top and your E is right there at the bottom. So it's clear enough they are not in the same state of what? Of vibrating. Okay. So this is out of phase. Okay, let me just write over here. Out of phase points. So we said the obvious one will be H and E. The next one that we're going to be looking at is what? It's H and K. The next one will be your likes of A and K, you know. All of those points are not in the same state of vibration with one another. So we consider them to be out of phase. All right. Also, with regards to the important terms, we want us to take a look at frequency. What is frequency? Okay, frequency is the number of waves that pass through a certain point in 1 second. How many waves did pass through in 1 second? Okay, we measure them using hertz and we abbreviate that saying this is the full hertz, and then we say capital letter H and the small letter Z. So if we want to calculate frequency, all right, we say F, which is your small letter F, is equal to 1 over period. So this is standing for your frequency. This is your period. Okay, and it has to be in seconds. Okay, period by definition is the time taken to complete one full wave. Okay, what was the time taken to complete? Mind you, one full wave has to consist of what? Has to consist of a crest, a trough. A crest, a trough. We say 1. A crest, a trough. We say 2. A crest and a trough. Not forgetting that your crest is the uppermost point and your trough is your lowermost point from the rest position. Okay. And also, that is just one. It comes with a formula. So it reads as frequency is equals to 1 over period. Okay. So most people, before I move on, with regards to period, most of you confuse that with just normal time that will be given to you because now it's given in seconds. However, you should understand that it's just the time taken to complete just one, not the entire pattern of the waves, but time taken to complete one full wave. Okay, it is also measured in seconds, just like your time, hence the confusion. It is easier. T is equals to 1 over F, which is your period, is equals to 1 over frequency. So this is the frequency. Okay, this is period. Still has to be in seconds, and over here it has to be in hertz. Right, and then we have wave speed. It's a speed. What is your wave speed? It is the distance traveled by the wave in 1 second. Okay, the definition itself gives the units, the SI units away. It is the distance that is traveled by the wave in 1 second. So your wave speed needs to be measured is SI units of what? Of meters per second, because you're looking at the distance. Mind you, the distance will be in meters, and then traveled by a wave in what? In 1 second, hence meters per second. With that one, you look at the information that is given to you. Was I given the distance that is traveled in time taken? If so, if all the variables tick the correct box, therefore you can use the V is equals to distance traveled divided by the time taken. However, if you have given the wavelength, you can divide your wavelength with the period, or you can multiply your frequency with the wavelength, which is our lambda. Okay, so you already know the SI unit for wave speed, for your frequency, for your lambda as well. So these are very important just in case you are given variables. However, they're not given in correct unit. So what you need to know is being able to move from one unit to another unit through proper conversions. Okay, that is actually a recap of what? Of grade 10 that we've done, being able to move from one unit to another unit. So when you're substituting, you don't forget that you've substituted the wrong SI unit. You just convert first and then substitute. All right. Now, I want us to take a look at now that we've learned about the terminology that we are going to use throughout, I want us to take a look at the multiple choice questions, how to choose them. Okay, also you're going to be exploring the long questions, how to answer them best, what to look for when we are attempting to answer questions on waves. Okay, bear in mind this is still our introductory lesson, so we're just going to take it easy in all the questions that we're going to do. Okay, so the first one is taken from the Gauteng Department of Education Relab, and it says, a transverse pulse is a single pulse, okay? A single vibration. Is it C, which is saying both A and B, or is it D that says neither A and B? So, when you are given multiple choice questions, there are two questions, or rather options to your answer. So, first up, you are given 4 options. So in these 4 options, 2 of them are entirely wrong. Okay, and then there is one distractor that is trying to distract you by all means from being able to identify your correct answer, and then there is your correct answer. Okay, so you should be very careful, putting some thought when you are trying to answer your multiple choice question. Don't just say which one is which, and then you just close your eyes and then choose no. You look at all your options that are provided to you. You say, okay, which ones are just going off? They're not related to what I want as an answer. You identify those. You say, okay, which one could be the answer? You identify that. But which one is a correct answer? That's how you learn to identify the correct answer in your multiple choice questions. Okay, so they're saying a transverse pulse. Instantly, when you think of a transverse pulse, what is running through your head is a definition of a transverse pulse. Okay, underlining the word pulse, being a single disturbance in a medium, transverse, meaning that the particles of the medium are propagating at a right angle to the propagation of what? Of the wave. Okay, so a transverse pulse is a single pulse. Okay, remember, pulse is a single disturbance. Okay, B, a single vibration. All right, C, both A and B are correct, or neither A and B. So the correct answer is C, both A and B, because it is a single pulse, it is a single vibration. All right, let's move right along, and then we have number 2, still on the Relab, Gauteng Department of Education, which I believe all of us have. Now they're saying, in a transverse pulse, the direction of disturbance is always, is it A, in the same direction as the propagation? Okay, that's where it ends. And then in the opposite direction to the propagation, to the parallel to the direction of propagation, or perpendicular to the direction of propagation. Goes back to the definition itself. Hence the importance of being able to define in full and with proper understanding. Immediately when you see your multiple choice question, after reading what is given to you, as you're going through the options that are provided to you, it should click, oh, this is what I'm looking for. Okay. Now remember, we had said in a transverse pulse, the particles of the medium are vibrating perpendicular. All right, to the what? To the propagation. Here's the propagation of the pulse moving in that direction, but the particles of the medium are at what? At the right angle to the propagation of the wave. So your correct answer that you're looking for is perpendicular, which is your D. Perpendicular to the direction of propagation. Okay. So why did we line out all the other ones? And in the same direction can never be in the same direction. So this took us out. Okay. In the opposite direction of the propagation, nope. Parallel, we are not talking about the longitudinal wave because the statement has correctly said the transverse pulse. All right, let's move right along. Number 3, the amplitude of the pulse. And immediately what comes into your mind? Amplitude is the maximum displacement from the rest position. Now, as you're going through your options, you are looking for what is similar or what is the same to what you're looking for. Okay, so option A, that is maximum displacement of the particle from the rest position. B, distance traveled by the pulse along the rope. C, distance from the start to the end of the pulse measured along the rope or slinky. And then D, displacement between the lowest position of the pulse and its highest point. Okay, so which one is our correct answer? The maximum displacement of a particle from the rest position. All right. Now, let's get into, now that we know how to attack our multiple choice question tool, we will continuously do, let's now attempt to answer certain questions on long questions. Okay, we have the figure below. This is taken from EC 2020, and we are going to make it our activity number 1 for the long questions. Right, the figure below shows a transverse wave motion. Right, that is, it's given to you. The speed of the wave motion is 20 meters per second, and its period is 0.02 seconds. Right, so let's attempt to answer the questions. What is meant by a transverse wave? Now, you're no longer identifying it in your multiple choice question. Now, you need to define it in full. All right. So, this is our number 1. Let's just get a black pen. It's a wave. Okay. So, a wave, so we start like that. A wave in which the particles of the medium vibrate at right angle to the propagation of the wave. wave. And that's how you get your what? 2 full marks. Okay. Let's go back a little bit. Number 2 is saying write down 2 pairs of points that are in phase. Remember on the last activity that we did? They have to be in the same state of vibration. Right. So in this diagram that we're given, in this transverse wave that's in motion that we're given, what are then those points that are in phase? Okay. A and D are in the same state of vibration. Let's just write it over here. So it's given as A and D, right? Someone else can come in and say B and F. They're in the same state of vibration over there. So how many was asked of us? 2. So we get B and F. Right. Write down. Now when a question says write down, it's more of you are identifying what is already in front of you. Okay, so it's not like calculate. When you're calculating, there has to be a formula, there has to be a substitution, and then there has to be your answer with units. However, when you are identifying, you're just writing down. Look thoroughly in what is given to you. There's just an answer right in front of you. Okay, so write down the amplitude of the wave in motion. First, before you are able to answer that question, you should be able to understand what is an amplitude. Amplitude is the maximum displacement from the rest position. Because it's easy to come and say, oh, okay, it is 30 centimeters. No. Because now your 30 centimeters is just moving from the top, passing through your equilibrium point, right down to the end where your troughs are at. But now your amplitude has to be moving from the rest position to the lowermost point or to the uppermost point, right? Because it is the maximum displacement from the rest position. In this case, this is our clue, right? So you have your 30 centimeters, right? So that means moving from the equilibrium going up, this is your 15 centimeters. This is the maximum displacement that you have. So that's how easy it is to just identify it like that. Okay. Let's look now at activity number 2. This one is taken from EC 2023. So it's recent papers that we are using as part of proper understanding in detail our theory today. So, taken as question number 5, it says consider 2 transverse waves P and Q, right? As shown in the diagram below. Or you take a look at what you have. You say, okay, what do you have? The first thing to do when you are given a diagram, you have to look at your x-axis. You have to look at your y-axis. So this is a position versus time kind of wave, okay? But it has 2 waves in them. So there's P and there's Q, and you're given a very nice key to say Q is dotted and P is in a solid line. All right, so that when you are answering with reference to whatever they're asking, you are able to just give a correct answer and not be mistaken or be confused between the 2 waves. Okay, so your position is given in millimeters, right? And then you have your what? Your 2 waves in there. So it's saying write down your one difference between wave P and wave Q. Right. What is the difference between wave P and wave Q? You look at your wave, you're like, okay. The difference is that with regards to the amplitude, I'm going to draw different amplitude with this one. So my amplitude for, what did they say, the dotted one? Q, is smaller because it's approximately a 10 millimeters. However, the amplitude for wave P, which is given in a solid line, is a bit higher than that of Q. So the displacements are not the same. Voila, you've spotted one difference. So the difference between P and Q is therefore what? Their amplitude. They have different amplitudes. Right. And then write down, we are at 5.1.2 right now, one similarity between P and Q. So what is it that is the same between all, or rather between Q and P? Let's look at it. As it goes up, due to the vibrations of the particle of the medium, but when they come to the rest position, they come simultaneously. So both Q and P are there at the same time. All right. They may differ in their amplitude, but they surely will pass the rest position together. This makes their wavelength to be the same. Because remember, what did we say the wavelength is? It is the distance between two successive or adjacent crest or two adjacent trough. In this case, they even indicated for us. So D and F, this marks as what? Is our lambda. This is our wavelength. Okay. So now we have what? One similarity is that they have the same wavelength. Keywords, that is different, similarity, that is what you're looking for. Okay. 5.3, label the points marked as D. Okay, you go back to what you're given. You're like, okay, where is D? Okay, here is my D, and it's not in pair with anything. It's just D over here. All right. So what was the lowermost point? It is trough. Remember I said you could just remind yourself by saying, okay, when you are counting your alphabet, you say A, B, C. It's closer. That means it has to be up, uppermost point. D, E, F, G, up until you reach your T right at the end of the alphabet. Then it has to be down. Right. So D is your trough. Right. E, let's go back a little bit so that we are able to see where E is. E is the uppermost point. What is it? I know you know it. It's crest. Very good. Right. How many complete waves are represented by Q in the diagram? All right, let's go back. But now we're focusing on what? On Q. Q, 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 dotted, that is. Remember, waves has to have crest, trough, crest, trough, crest, trough, in that order. 1, 2, sorry, let's count again. 1, that is 1. 2, in fact, let's use a different pen so that you are able to see. Crest, trough, 1. Okay? Crest, trough, 2. Crest, trough, 3. Right. So there are 3 waves that are there. Okay? So complete waves that they are. So there are 3. Okay? Write down the letters that represent any 2 points that are out of phase. Okay? Let's go back to the diagram. Any 2 points. Are we specifically looking at any? Yes. Okay? Let's go back a little bit. We can say A and B. You can see where A is at. You can see where B is at. Someone else can come and say B and C. because they're not in the same state of vibration. Someone else can come and say D and E, E and F. Okay, remember, you cannot just say point. They have to be going in what? In pairs. Okay, so points that are out of phase, we're mentioning 2 points, right? So this is A, we say it's A and B, and we also counted C and D. Right. These are just easy marks. As soon as you know the definitions, as soon as you know how to find those answers that you're looking for, then you just come to your paper, you start by attacking your paper, because the theory work was done understandably so. Okay, one wavelength apart. Which ones are showing one wavelength apart? They even showed it to you. D and F, B and D, A and C, okay? All of these ones, because we said it is a distance between two adjacent what? Adjacent crest or troughs. So between here and here, this is your wavelength. Here and here, this is your wavelength. Okay, so you can just take A and C. Okay, someone else can come in and say, no, ma'am, I think I like B and D. All right, that will still be very much correct. 5.6. For the wave pattern P above, determine the amplitude. Can you tell that? You are determining the amplitude for wave P. Let's just go back a little bit. For wave P, here is your P. P is our solid line. You look at the maximum point that there is. So here it is 15. So it is 15 what? Millimeters, because it is given as what? Is millimeters. Okay? So 15 millimeters. Okay? So because you're looking at the maximum displacement from the rest position. Okay? And then calculate the frequency. Right. How do you then calculate the frequency of your wave? All right. So for P, because we are still looking at what? At wave pattern P. All right. So what do we do? All right. You can come back to your, there it is. So we're looking at 5.6. We are specifically at 5.6.2. You said frequency is equals to 1 over period. Because that is how we said, that is how we're going to calculate our period. So we said 1 over, so what is period? It was not given to us, but then now by being able to define it, we'll be able to just what? To point it out. Okay, period is the time taken to complete one full wave. Okay, in this case, for me or for us together, because we're doing this together, to complete one full wave in here, it will take us what? 20 seconds. Another 20 seconds, I'm completing another wave. Another 20 seconds, it's taken to complete another one full wave. So the time taken to complete one full wave is therefore 20 seconds. Why am I saying 20 seconds? Because here is in seconds. And for me to be able to complete from crest and trough, which marks my full wave, is taking me what? 20 seconds. Okay. I don't have my calculator with me right now, and then you say what is 1 divided by your 20. It will then give you your answer in hertz, because your hertz is the frequency, is the SI unit for frequency. Right. Now 5.6.3, the wave speed of the wave, right? So how can we calculate the wave speed of the wave? Remember how we defined it. It's the distance traveled by a wave in 1 second, right? I said to you, depending on what is given to you, you are able to what? To be able to calculate the wave speed. There are 3 different formulas that they are. You can choose the one that best give or be able to use the variables that are best presented to you. All right. So with this one, I can do it in this way. 5.6.3. My wave speed is given as V is equals to frequency times lambda. Okay. So I already have my frequency, which is the answer I got from the top calculation. I already have my lambda. However, there's something wrong with my lambda. Here's what. My lambda is given in millimeters. And I know that my lambda needs to be in meters. Therefore, we go back to knowing how to convert. Grade 10. Remember when we did this together in grade 10? We said kilometer, we said meter, we said centimeter, we said millimeter. Okay? That means you have to be able, when you're moving from a big unit to a small unit. So what we're doing, kilo means 1,000. You said times by 1,000, times by 100, times by 10. Why? Because when you're moving from a bigger unit to a smaller unit, you multiply. However, when you're moving from a smaller unit to the bigger unit, you divide. Therefore, when the arrows go to the other direction, you say, okay, now I am moving from millimeter. Here is your centimeter over here. Here's your meter. I'm just writing it exactly as it is appearing at the top. Right. So, but however, same factor, but now I'm dividing. So this is divided by 10. This is divided by 100. This is divided by 1,000. Right. And then you ask yourself, what do I want? And which unit am I moving to? And where am I going to? Your answer is simple. You say, okay, I want these millimeters that I have. That means I'm there. And I want to move to meters. Okay. I'm moving from millimeters, and I'm going to meters. That means I am going in that direction. That means I need to divide. That is the first thing you've analyzed. I'm dividing. But by what factor, you ask yourself? You look at how many zeros you have skipped. So how many zeros did we skip? Because now we identify, okay, I'm moving in that direction. That means I am dividing. Right. But how many zeros have I skipped moving from millimeters to meters? I've skipped 3 zeros. That means I need to divide by 1,000. Okay. That is how simple it is. So with regards to this 60 millimeters that we have here, therefore we need to then say 60 divided by 1,000 so that we can get our answer as in meters. So we say 60, therefore 60 millimeters divided by 1,000, because we've jumped 3 zeros in here, and then we get our answer as 0, I do not have my calculator, I'm just doing it at the top of my head, 0,006 meters, assuming this is your answer, right? And then this is the answer that you substitute as your what? As your lambda. Right. So now you have your frequency, you have your lambda, and you'll find your answer in meters per second. Why is it writing in a different way? In meters per second. So if you're not vigilant enough, somebody can just take the 60 millimeters as it is, forgetting that we had said wavelength has to be in meters. So understanding the SI unit of all the variables that you're dealing with is very, very important. Okay, so I hope this one was easy enough for you. All right, so let's move right along. So this one is a special one. This one is the one that now I want us to do, looking now at the theory work that we've done together. All right, so we are on learning activity number 3. Consider the following wave and answer the questions that follow. Very important to read what is given to you, because most answers are usually there. Okay, so there's our wave. So you've got a wave, there's propagation of the wave that is given to you. Remember, I said to you, it's very important to look at what you're given on the x-axis as well as your y-axis. Again, they're asking us to define a transverse wave. And I know you know it by now. It is a wave in which its particles of the medium are vibrating at the right angle to the propagation of the wave. That's how simple it is. Full marks, that is. Then 1.2. Distinguish between a wave and a pulse. Okay? You start by a pulse. You say, okay, as you're distinguishing, if you are unable to distinguish without writing a paragraph, just write it in a tabulate kind of form. Tabulate it. Have a pulse this side. Let's just do it. Okay, we don't have space. Let's just say this is how you do it. This is how you properly differentiate. Okay. So this one you just write, this is my pulse and this is a wave. Then you define the two. Right. Nicely done. So a pulse is a single disturbance in a medium, but a wave is a continuous disturbance in the medium. So it's no longer just one single disturbance. It's a continuous periodic disturbance in a medium giving succession, or rather a train of pulses. All right. With reference to the diagram of the wave shown above, write down the letters that indicate that indicates amplitude. Amplitude. There is even a dotted line. So write down, with reference to the diagram of the wave shown above, write down the letters that indicates the amplitude. So here's your amplitude. I and B. So let's just say you're moving from I to H or I to B. To B. Okay, someone else can come and say it's okay, no, it can't be this one. So it's I to B. One wavelength from the position of B. From the position of here, what is then the one wavelength? You're looking at from here, because it has to be two adjacent crests that they are, or it could be trough as well. So it's from B to E. That is marking one wavelength. But we can't take another one, because now they had said with reference to what? From position B. So it's what? B and E. Okay. Easy, easy, easy. This one, after doing it together, this is for you. And I believe and trust that you're going to find it fun. So first up, we are going to be defining the terms. Try to define them fully so that when it is time to put it into practice, when you have to identify, when you have to calculate, it is very easy. So from 1.1 up to 1.10, we have a pulse, we have a longitudinal pulse, we have wavelength, we've got period, we've got trough, we've got transverse pulse, amplitude, frequency of the wave, crest, and wave speed. Believe in me, we covered all of them, and I know you know them. Number 2, differentiate between 2 points on a wave that are in phase and out of phase. All right? So how can you differentiate between the points that are in phase and the ones that are out of phase? All right. Number 3, study the diagram of a transverse wave below and answer the questions that follow. Here's the transverse. Remember what I taught you in terms of studying the actual diagram that is given to you. So in this case, the y's are not labeled, the x's are not labeled. So we're just looking at the propagation of the wave itself. So label the parts A, C, E, and F. A, C, E, and F. Easy peasy. Now, write 2 letters that represent 2 points that are on the wave that are in phase. So in number 2, you have to differentiate. Remember what I taught you about distinguish, differentiate, tabulate. Just tabulate so that you are always on the safe side. Right. And then right there in 3.2, how is it different from number 2? In 3.2 now, you need now to point the actual points that are in phase. You're not defining them no more. Okay, you are actually pointing them out that this one is in phase with that one. This one is actually in phase with that one. Okay, number 4, calculate the period of a wave whose frequency is 50 hertz. How nice is this? You're calculating a period of a wave and you are told the frequency. So that means you just simply say period is equals to 1 over frequency. Frequency that is given to you is in correct unit. Substitution, answer with units. Right. Calculate the frequency of the wave. All right. If its period is 0.5 seconds. You say, how do I calculate my frequency? Frequency is therefore given as 1 over period. Period in this case is given to you as 0.5 seconds. Correct unit that they are. Time taken to complete one full wave. All right. Number 5, which is saying calculate the speed. Has to be in meters per second. Okay. Of the periodic wave disturbance that has a frequency of 3.5 hertz and a wavelength of 0.7 meters. Okay, you said, because you were taught by me, you said speed is equals to frequency multiplied by lambda. Substitution, formula, substitution, answer with units. Right, so I'm sure you're going to find this fun to work on. It was taken from FS revision book, Free State that is, and I hope you have fun attempting all these questions. Okay. I want to end today's lesson by a quote of one of my favorite authors, Robin Sharma. He's saying this time, stop managing your time, but start managing your focus. What is it that you're focusing on? Realign, refocus on the things that you choose to focus on. Hope you going to have a lovely time attempting all these questions. Have a wonderful time. Thank you.